Thank you for joining me for Chapter 5 in our lecture series. Today we're going to talk about volcanoes and volcanism, and in this lecture we'll be talking about how volcanoes are constructed, how they erupt, how they produce ash and gases, and basically how we know if one is going to become active. So we, as geologists, identify the basic types of volcanoes by their eruptive styles, the composition, and their shape. Although all volcanoes are unique, we can identify three different types. There's a shield volcano, a cinder cone, and a composite volcano. We'll talk about all three. We're going to talk about Hawaii, Alaska, and the Cascade Range, the Pacific Northwest. We'll also talk about the Ring of Fire in association with those areas. We'll talk about eruptions that have occurred in the past, documented eruptions, and we'll talk about the explosivity index. Once a volcano has erupted, we will identify how big the eruption was based upon a certain index. And then we're going to talk about how most volcanoes are located by the divergent and convergent plate boundaries. So here you see a volcanologist measuring the temperature, or basically walking across mafic lava. The long spear-like thing that he's holding is to check in front of him to make sure he doesn't break through and fall, well, obviously down. There's a river of lava underneath him. Looks like there's an arch where it's cooled. This guy's pretty brave, but you know, when we talk about volcanism and how eruptions occur, it's always, or we identify it by the association between the magma and the gases that come to the surface. Some magma erupts explosively and produces pyroclastic material. This is pyroclastic means fire-broken rock, and others erupt with well, like a lava flow that you see here. We don't have a lot of eruptions. There are about 12 or so erupt per year, and most eruptions that occur are usually in areas where we know there's going to be eruption, like Hawaii or Mount Redoubt, or areas like that's in Alaska or along the Aleutian chain. A lot of the eruptions start and they will continually erupt even though the lava is not coming out the whole time. It's still considered the same eruption if it lasts for a month or, you know, several years. There's some volcanoes like in Hawaii that will erupt for multiple years and we consider it the same eruption. Question that often comes up when you're studying volcanoes is what is considered an active volcano. Here we have a vent, or an area where the activity has broken the surface of the earth, and in this case we have a lot of volcanic gases coming out of the ground. This is appears to be a new volcanic vent because they've blocked it off with barricades so that people don't approach it, because a lot of these gases that come out of the ground are toxic and you don't want to breathe them. In most cases they dissipate and they're not going to harm you, but some are heavier than air, and so they can collect in low-lying places and suffocate people. This is common in areas where there's a lake and a caldera and you get an eruption, and since that's an enclosed area, people can suffocate. Eruptions primarily produce carbon dioxide, nitrogen, sulfur dioxide, and these hydrogen sulfides. That's the rotten egg gas. There are small amounts of carbon monoxide, hydrogen, and chlorine. The chlorine gas and the sulfates and the sulfur, actually the sulfates would cool the planet, but the chlorine gas contributes to the deterioration of the ozone layer. It's why we stopped using specific refrigerants, because they contained chlorine that used up or affect the ozone layer, which is O3. And this is a concern for, well, us, because we're not really well protected from the sun. If we're not wearing sunblock, we can end up getting sunburned from the ultraviolet radiation. We also have areas where the sulfates, or the sulfur gases, when we see a very large eruption, it will cool the global climate for 1 to 2 years. For example, when Mount Pinatubo went off, I think it cooled the planet 1 degree something. I think it's about 1 degree for a couple of years, up to 4 years. Primarily, when we're talking about specific kinds of lava, we break it up into two different types. So we have the mafic lavas. Here we have a lava tube. Mafic lavas are very warm, and they flow rapidly because they're warm and they have a low viscosity, which means that they're runny. And in this case, we have a lava tube that was filled with lava at one point, but since it flowed out before it solidified, you have this open space. And this is what this guy's walking over. This is a lava tube that's formed, and it's going to not fill in with lava because it's going to empty out probably through another vent somewhere else. Here we have lava that is a little more viscous, but not a lot. We have Aha lava, which is double A. It's what the Hawaiians call it, and it's a blocky, angular type of lava that has a lot of fragments in it. And it's not a violent eruption, although it looks like it on the photograph on the left there. It tends to just roll out of the ground, and some gases are escaping, and then it also has pahoho that can be associated with it as well. In this case, the pahoho that you see on the right, it's kind of like Caro syrup or taffy or something like that. It's pretty thick, but it's still not as thick as the felsic lava that we get on land. It's not as thick as the lava that we get on the continental crust, which is the felsic lava. Another type of lava, mafic lava, that forms under the ocean is called pillow lava. And it's pillow lava because as it comes out of the ground, the pressure changes and it expands rapidly and cools rapidly, so it produces these pillow-shaped structures. And these are primarily found on the divergent plate boundaries, and they make up the ridge when we talk about the ridge push slab pull idea in plate tectonics. This pillow lava is primarily what we consider making up the ridge. And they are primarily basalt. So when we talk about basalt, it means that they have very small crystals. The crystal size is less than 1 millimeter, and it's often, you can't see it with your eyes. You have to get a microscope out to see the different crystals because it cools so rapidly. As lava cools, it produces joints, which are cracks in the rock. It's not the same thing as a fault because this is only in the external portion of the Earth's crust. It doesn't travel deep into the Earth's crust and through several different rock layers. Here we just have columnar joints, which are these hexagonal sort of cracks, and I often see these out in Colorado when I'm out doing research. They look like Devil's Postpile, a national monument. I see them in Colorado. I have some pictures. Maybe I'll share them with you at some point. But they're fractures and they just fall apart, just like they are shaped. You end up with these hexagonal boulders type of rocks that are underneath the lava tube. And then the one on the lower right there, that's probably the Causeway of the Gods, which is going to be found in Ireland. And if you guys remember, I don't know if it was 3 years ago when we were watching the Summer Olympics, they had a children's choir singing on the Causeway of the Gods, and they were standing basically on what you see in front of you. These joints occur most often in basalt and andesite. These are lava flows because they're gonna cool rapidly, and if they're cooling underground, they don't form these structures because they're going to form larger crystals. It's going to take much longer for them to cool, and you end up with a gabbro or a granite rather than an andesite or a basalt. So what basically is a volcano? Well, a volcano is a hill or a mountain that develops around a vent where lava or pyroclastic material or gas erupt. Usually it's all three. These pyroclastic materials can vary in size, and the sizes will determine often what kind of volcano you have. In this case, this is a stratovolcano or composite volcano, which will have a variety of sizes of material. It'll have ash that's less than 2 millimeters. If you remember the planes going over Iceland, we're watching out for ash because when it produces a lot of ash, those really small silicate structures, silicate minerals get into the engines and grind them up. It's sort of like putting sand in your car engine. It's not very good. Then you have lapilli, which is 2 to 64 millimeters, which is primarily what you see in a volcanic eruption. Most of it's going to be ash or lapilli. You do have some bombs. It takes a little more energy to throw them, and they're greater than 64 millimeters. And then, of course, the blocks are these big solid pieces of material that can be thrown out of a volcano. We often see those in the horror movies or the catastrophe movies, but they're greater than 64 millimeters. The volcanic ash can be transported long distances. If you look at on our webpage, you'll see where I have Yellowstone, the old eruptions from Yellowstone, and some of those cover the entire North American continent, or pretty close to it, or at least the United States. So we have a picture of Crater Lake. And Crater Lake is a large caldera that collapsed as the magma chamber cooled and contracted, because as it cools, it's going to become more dense, take up less space, and the top of the volcano collapses. And in this case, it filled in with water, and then you have a secondary eruption from later in time, and you end up producing Wizard Island, which is the island you see in the center. It's a beautiful area. It's also one of the deepest lakes either in the world or in North America. Definitely North America, but I think it's also one of the deepest lakes in the world, freshwater lakes. So how does this happen? Well, if you look on the right, the slides on the right, you have Mount Mazama. It's a volcano. It's an elevation about 3,500 meters. And it's erupting, and you have all of these fissures, these vents coming out, erupting all over the place. Multiple fractures are produced, and then you get eruptions along the sides as the center collapses. And then at the very end there, that's what I just said about Wizard Island. You have one more lava vent that comes up to the surface. And you have a few minor eruptions filling in one area of the caldera, and the rest is then filled in with sediment and water. And if you notice the rim of Crater Lake, it's 2,000 meters, so the actual elevation of the volcano dropped from 3,500 meters to 2,000 meters, which is a pretty significant disruption. So let's start talking about our volcanoes with a shield volcano. These are the largest volcanoes known. They are usually composed of basalt and the darker mafic type of lava, because they come from deep down in the earth. So do the other volcanoes, but in this case you have a very large magma chamber, and you have several vents coming to the surface. You have the summit caldera, which in this case in the picture is the central vent. It's the largest lava flow when it erupts, and then you have the flank eruptions that can often come off to the side, and we'll see some pictures of that later on when we look at Idaho and Utah and Wyoming. The Hawaiian volcanoes are shield volcanoes. So if you look at the Hawaiian Islands, they're shield volcanoes. They're very large. If you think about the size of the Hawaiian island, it is the tallest mountain in the world. And in this case, it would be Mauna Kea, which is one of the mountains or one of the volcanoes on the Hawaiian island, on Hawaii, and it, I believe, is taller than 33,000 feet if you go down to the base to the top of it, which is obviously under the ocean. But it is the tallest mountain that we have in the world. It's not in elevation, it's how tall it is from the base to the top. It's actually, I think, 13,000 feet even if you start at sea level. And what's amazing by that, or amazing to me anyway, is people go skiing in Hawaii. We don't normally think of, the Hawaiian Islands and skiing, but it snows at the top of those islands or the top of those mountains, because they're so high, which is pretty cool. In most cases, when we're talking about the shield volcanoes, they are the least dangerous to humans because their lava tends to be mafic, which means it tends to be hotter. It's also runnier. It's not explosive, and it doesn't produce a lot of ash. So those things that well, to a certain extent, it doesn't produce a lot of ash. Obviously, the um, volcanoes, the shield volcanoes, the divergent volcanoes that we have in Iceland do produce a lot of ash, but in most cases, they don't produce that much ash. And of course, we have the largest shield volcano in the solar system, and that would be Olympus Mons on Mars. I think it's like 4 or 5 miles in height, in elevation. So we'll move on to talk about cinder cones. So that was shield volcanoes. Now we're going to talk about cinder cones. Cinder cones aren't of much concern when we're talking about humans and the effect they have on humans, although the picture on the right looks pretty drastic, but that's usually due just to fire and other things. Um, Cinder cones are pretty small. They are dry eruptions that produce or spew out, looks like scoria. If you guys know what, or scoria, it's the kind of rock that you put around plants, and it's red, it's very lightweight, and it's full of holes. And you have some in your collections if you look at it, or vesicular basalt would be another one that comes out of these cinder cones. They're not very tall. When I was in Utah, I used to spend a lot of time playing in southern Utah around the cinder cones. They're really fun to play on unless you fall, because they're basically glass. You get pretty cut up. Well, you get just really bad road rash, but it's deeper than the normal road rash I guess you get if you fall off your bike. But they are relatively short as far as mountains or volcanoes go. I think the tallest ones are, I think in the book it says 400 meters tall, so they're not very tall, which is approximately 1,200 feet, around there. The last volcano type that we're going to talk about are composite volcanoes or stratovolcanoes. The reason we call them stratovolcanoes is because they're very tall. They get into the stratosphere, in quotes. So we call them stratovolcanoes. They are a composite, which is also why we call them a composite volcano. They're a composite of pyroclastic material and lava. So you get these areas where you get a lot of ash and lapilli and some other stuff coming out, getting blown out of the volcano, and it covers the slopes. And then you also get a lava flow. It's usually an intermediate type of lava. It's not mafic, it's not felsic, it falls into the intermediate range, and they tend to be explosive because the lava that comes out of composite volcanoes is thicker, which means it has more silicate in it, which produces more force when you build up pressure behind it. It doesn't release as easily because it's not very runny, and then you get an explosive eruption. The last type of volcano that I'm going to talk about, we don't normally consider the three major ones when we talk about, shield volcanoes, composite volcanoes, and cinder cones. In this case, it's a lava dome, and this is where you have a volcanic pipe or a vent, and the lava that comes out is very thick. It tends to be the felsic type, it's intermediate too, but it tends to be a high silicate concentration, but it's so thick that it just piles up around the vent. And they can be quite large, and you end up with a rhyolite, which is the lava version of granite. So you have granite and rhyolite, and it's very light colored, and they're pretty massive. And there's a lot of lava domes that people climb in California, very famous areas. In this case, I think in the notes or in the book they talk about ejecting. I think they call it Nue. I can't pronounce it. Nue ardentis, which means like new teeth or something like that. It's in French, and obviously don't speak French, but there are hot clouds of pyroclastic materials and gas that get thrown out of these, and it's not very common, but it can cause problems. And the last one that we're going to talk about are the supervolcanoes. Supervolcano eruptions haven't occurred in known history, which is the written word. They actually haven't occurred when humans sort of have been on North America or pretty much anywhere out of Africa. It's happened, I think Yellowstone erupted 2 million years ago, which would have a dramatic impact on the world, because it would cool the temperatures and spew out a huge amount of material. If you look at the largest eruption from Yellowstone, they hypothesized that it produced 600 metric, or not tons, it's 600 square miles of material. And this is over a long period of time. It doesn't just happen all at once. But that would be like taking a piece of rock and running from Detroit past Chicago, then up north past the Upper Peninsula, or about to the Upper Peninsula, no, even farther, 600 miles square, and then going 600 miles into the air. That's pretty amazing considering the chamber that produces it. I mean, it's pretty big. It's much bigger than 600 square miles, but it does go down 450 miles into the Earth, and that's what you see on the left side here. And it's just astounding. I used to go and hang out in some hot springs when I was a kid that were actually heat from Yellowstone, but I lived in northern Utah at the time, so this is a pretty expansive magma chamber. The last thing I'm going to talk about, although I did say that about Yellowstone, but are these fissure eruptions and basalt plateaus. So if you look, I'm going to grab a pen, my mouse. If you look, this hill that you see right here is actually the Snake River. It's great fishing if you're a fly fisherman. This area right here is all basalt. You can kind of see it right here on the side of this hill. It's a very dark mafic type of rock, and these lava flows were enormous. So the basalt plateau that we have in Washington, Oregon, Idaho, and it actually goes down into California was an eruption that occurred I think a billion years ago or several billion years ago. I'd have to check, and it was called the British Columbia Shield Cone. And it was a fissure eruption where the erupting lava came out of a fissure between a continental plate and the oceanic plate. And if you look, it was up in this area. It goes off the screen here, and the flow goes all the way down like this. I mean, it was a huge flow. You can see right there, it covers multiple states. And it obviously wouldn't be happening today because the radioactivity that drives the heat in the planet to make eruptions such as these is no longer, well, the Earth isn't that hot anymore. But it's a pretty astounding eruption. Here we have an image of the plates, or actually the volcanic activity around the plates. This would be the Ring of Fire. We call it the Ring of Fire because we have these volcanoes that run along the rim of the Pacific. They go all the way down, and then this is a divergent plate boundary down here. What's interesting about this is we have the North American and the Eurasian plate and the South American plate covering up the Pacific plate. That's why we have so much volcanic activity in the Pacific, because the Pacific Ocean is getting smaller. And if you look right here, this is a divergent plate boundary, and the divergent plate boundary is pushing this material this direction. Now, obviously up here as well. And the Atlantic Ocean is getting larger. Eventually the Atlantic Ocean will be the largest ocean, the Pacific will be the smallest or enclosed completely, in North America and the Eurasian plate and South American plate will be connected, and we'll have another supercontinent like we did 250 million years ago. So what is a result of this expansion of the continents over the Pacific is a very active volcanic zone. We have the Cascade Range, which is primarily volcanoes. The Cascade Range goes all the way down into Northern California. And in this case, in this slide, they show, well, they show the Cascade Range. They show how the subduction of Juan de Fuca underneath the North American plate produces most of this volcanic chain. It's a continental volcanic chain. And in the center there you have Mount Adams that's erupting, and that's a pretty standard eruption where it erupts and throws ash into the air. On the right you have Mount St. Helens, which totally unexpected blew up to the right. It sort of, well, in this case it's the perspective, but in our slide it's to the right. And the whole wall of the caldera collapsed and produced a huge amount of ash, and the eruption didn't really spew a lot of ash really high up into the air, although there was an ash trail coming out through Oregon and Washington and into Idaho. But it was a pretty geographically, or at least geographically changing eruption. Changed the whole physiography of the mountain. And as I said earlier, we have this igneous activity at the divergent plate boundaries that occurs underneath the ocean, but we do have some volcanic activity that is above the ocean in places like Iceland, where it occurs above sea level, and we get a lot of these eruptions that affect air traffic. We also have, I believe, eruptions in North Africa in one of either the Rift Valley or one of the valleys there, because it is actually a divergent plate boundary, and as more lava is pushed up, because it's a mafic lava, it's more dense than the continental crust around it, it will sink into the ground. Eventually it will fill in with ocean water, be a shallow sea, sort of like the Red Sea, and eventually the African continent and the Eurasian continent, along with the Middle East right there, will separate, and you'll get another ocean forming there. You can't predict if it's going to continue forever, so it may actually stop and fill in. For example, that's what when we talk about these faults and stuff that we have in Missouri, that's actually an old divergent plate boundary that sort of misfired. It just stopped going. We don't know why, so we didn't split the United States, or in this case, the North American continent. Otherwise, there would have been there would have been two continents, two North American continents. Going back to the slide previously, or not the slide, but the picture of the Ring of Fire, we see that most of the igneous activity is at these convergent plate boundaries. So I think it's like 60% of the volcanism is on the Pacific Rim. We do have like 20% of it, which would be in the Mediterranean, and then the other 20% around the world in various places, hotspots, things like that. Most of this lava produced is mafic lava, which means it's very dark colored and dense, has a lot of metals like magnesium and iron in it. Then we have, this other 20%, which are mafic hotspot volcanism, and the Hawaiian Islands are one of those areas where the volcanoes originate at a stationary mantle plume that comes up through the mantle, through the crust, and doesn't move. It looks like the Hawaiian Islands are moving because the plates are, but in reality the hotspot doesn't move. The plates move over the top of it, and then they carry the islands that are produced away from the hotspot, and eventually they erode away because they get far enough away where you no longer have vents connecting them to those islands, and they erode away, and you end up with these island chains eroding down into flats like guyouts and seamounts, or guyouts basically. That's Midway Island. If you look, that's in the Hawaiian Island chain. At one time, Midway was a very tall island that has been eroded away because it's no longer connected to the Hawaiian hotspot. So what are the most dangerous manifestations of volcanoes? Well, we kind of talked about it. It's lava dome eruptions with huge amounts of pyroclastic material if they are violent. In most cases, lava dome eruptions, because it's felsic lava, it tends to be really thick. It's so thick that it doesn't erupt violently. In this case, we have I don't think we have a case here, but we do have lava dome eruptions where you have huge amounts of pyroclastic material, and it's Nuae ardentis. I can't say that, it's in French again. or a dente or whatever, and it can cover large areas with this hot ash, and basically people can be covered. And think of Pompeii in a way. Pompeii is actually a volcanic eruption, a stratovolcano eruption, but same kind of thing happens where you get this hot ash covers people rapidly and they suffocate and burn. It's a very kind of drastic way to go. And the other one is the lahars, which I haven't really talked about much, but they are very dangerous because it's basically a hot, superheated mud flow. They move very rapidly. You can't swim on them or anything. You'd burn up. And that's when a volcano is erupting. The lava is 900 degrees because this usually happens in these stratovolcanoes where the snow fields are, whatever, are located, and they melt that rapidly, which produces a mud flow that is cooled, yes, a little bit, but still it can be 400 degrees and traveling at 100 miles per hour. So these are things you have to worry about. And of course, we have a sign right here where the arrow is, where CO2 can be a hazard as well. And then on the right, we have it looks like that's probably Mount Pinatubo or something like that when it was erupting. Huge amount of ash coming out of the ground. So how do we determine the size of the eruptions? Well, we use a volcanic explosivity index, which means we look at the amount of material that is ejected, or the amount of material that is erupted, and the cloud height. So in this case, I will illustrate with another slide, but in this case, most of the eruptions that we have been small to moderate. We haven't had any really explosively huge volcanic eruptions in some time. And if you look at the names underneath each one of these, and I'm going to go to the next slide, the Strombolian, these are all periods of geological history. The Strombolian, which we didn't see a lot of activity, these are volcanic explosivity indexes of 1 to 3. They're small eruptions. Think of Mount St. Helens. Then you have the Vulcanian, which are volcanic explosivity indexes of 3 to 5. That would be almost Mount Pinatubo, maybe. It's getting there. And then the Plinian, which are volcanic explosivity index of 4 to 7. These are huge eruptions. These would be the supervolcanoes. And these are cataclysmic sort of eruptions that change the way the planet functions. So, how do we predict if we're going to have one of those cataclysmic eruptions? Well, we really can't predict exactly when they're going to erupt, but we know that they're going to erupt based upon seismic measurements primarily, because right before an eruption you have something called an earthquake swarm, and you can have moved from 10, 15 earthquakes. These are very small earthquakes, not the kind that we would feel, but they're not perceptible to us, but they're still moving the ground a little bit. And what that is the movement of the magma in the magma chamber as it percolates. I'm putting that in quotes in my head. It percolates up from the ground and moves through the country rock. As it does so, it moves it and it creates tremors. We have seen Yellowstone move from an average of 30 to 50 tremors a day to several tens of thousands to even up to 1 million in a day. We don't really know what's going on. That's why they were worried. We know that it's bulging. We know that Yellowstone is changing, and it is of some concern, but I don't think it's going to go off in our lifetime. And if it does, there's not much you have to worry about because everything will be pretty decimated. So, something you just have to worry about. But what geologists do is they usually look at seismic measurements. They study the history of the past. So in the slide you'll see study of past volcanic deposits, and they'll date them, and we know that every 600,000 years we have an eruption in Yellowstone approximately. And then they'll look at the temperatures of the changing material underneath. They'll do gravimetric magnetic field studies because the gravity shifts, because we know this tends to be dense stuff, which means it's heavier and has more gravity in a sense. It attracts things to it because it's denser, more gravitational pull. And then, of course, we look at satellite remote sensing, see if the ground is changing with either deformation studies or elevational changes. We also can look at the gas sampling and temperature measurements. I mean, a lava sample collection, but at that point you're already having an eruption. In this case, Yellowstone hasn't erupted in a long time, and we don't want it to erupt anytime soon. So to summarize, we have volcanoes are determined by their eruption characteristics and their parent material. So we have 2 kinds or 3 kinds of material, which would be the mafic lava or mafic magma, the intermediate lava or magma, and then the felsic magma or lava. Now remember, the mafic is very dark, it's full of magnesium and iron, and then as you go through Bowen's reaction series and those crystals form that are very stable, they fall out very deep in the earth, and you end up having more silicates in the material that gets near continental surface. And so you're moving from mafic to felsic. And in this case, we have different volcano types that really do form depending on the type of material that is in them. The shield volcanoes tend to be the basalt or the less viscous type of material, so it spreads out. It still gets very tall, but they're very large volcanoes. Then you have the cinder cones, which tend to be mafic, but they're also very dry. They're not very hot. They have a lot of gases in them, so you produce vesicular basalts and scoria, and it comes out basically blown out, a little bit of lava, but mostly cinders. And then the strato or composite volcanoes, which is a combination of this pyroclastic material and then the lava itself, and that lava is usually intermediate or felsic. But then if you get too far into the felsic, because it's has so much, not too far, that's the wrong way of saying it, the more felsic it becomes, the lava becomes, the more thick it becomes, because it has more silicates in it, you end up producing a lava dome instead of a volcano. And then the last thing, the volcano belts are found where there is an interaction between the oceanic and continental plates. Those are convergent boundaries. A lot of melting, as I call it the boot effect, just like when you put your boot down in mud. All of those particles interlock because of the pressure, and you're held up. But the minute you lift your boot, all of that becomes a liquid because you've changed the pressure and you've changed the temperature, because we don't really normally think of that, because of the pressure and temperature are related, and it becomes liquid and your shoe gets pulled off. Well, that's the same kind of thing that happens when you have these large plates subducting underneath the continental plates. So we have these oceanic plates. As they drop, they create a suction as they drop, which melts the surface, which is where this magma comes from. When it's being melted, because it's mafic, you basically have the mafic lavas deep down in the earth, and as it comes up and you get a changing in pressure and temperature, different minerals drop out, and you end up getting a change or consistency, a change in consistency of the lava itself. And then, of course, the volcanic eruption characteristics determined by historic standards, which give us the VEI, and we then can determine how would we respond if certain volcanoes were to erupt. Thank you.